Muy buenos días. Tengan todos ustedes. Gracias por su asistencia. Una disculpa, tuvimos una breve por cuestiones de conexión, pero les agradecemos mucho el tiempo por estar en esta sesión. El día de hoy me acompaña Narayana Balu, quien es de soluciones en Dassault Systems, en Simulia, y él es quien va a dar este webinar. Él está ubicado cerca de Boston y su experiencia se basa en electromagnética de alta frecuencia, especialmente en la simulación bioelectromagnética y multifísica para aplicaciones conocidas como Life Science. Él brinda asistencia técnica y servicios de ingeniería a los clientes y ayuda a de las soluciones de bioelectromagnetismo de Simuli. Un poco de sus antecedentes. Narayana comenzó como ingeniero de aplicaciones en CST en el 2014. CST es la compañía que desarrolló esta tecnología de electromagnetismo y esta compañía fue adquirida por Dassault System en 2016 y ahora se encuentra totalmente integrado dentro de las soluciones de Dassault desde el 2019, desde febrero del 2019. Un poco también de información académica. Narayana es ingeniero en electrónica y comunicaciones, graduado en el NIT en la India en el 2009 y tiene una maestría en ingeniería eléctrica e informática en la Universidad de Massachusetts en 2014. Y su trabajo de tesis pues, prácticamente se centró en el modelado computacional de ondas electromagnéticas sobre superficies del océano. Cabe mencionar que este webinar va a ser desarrollado en. Si hay alguna duda, no hay opciones del webinar que permiten hacer preguntas. Entonces, con toda confianza, hagan las que sean necesarias. De la sesión, haremos estas preguntas y respuestas, pero si en el proceso hay alguna pregunta, las vamos a ir almacenando y al final daremos respuesta a todas estas dudas. Narayana, I'm saying that at the end of the webinar, we can have a Q&A session. And welcome and let's begin.
Okay, thank you, Oscar. Good morning, everybody. My name is Narayana Balu, and I am a solution consultant for CST within the Simulia brand of Dassault Systems. We will look at a general overview of electromagnetic simulation for design and analysis of antennas and microwave RF components. Please feel free to post questions in the webinar chat window, and we will try to address these questions in the webinar. For the presentation will be as follows. First, we will look at the application areas that Simulia CST Studio Suite addresses and the solver technologies that it provides for 3D electromagnetic simulation. Next, we will see some examples of how antennas act as the key enabler for internet and 5G communication. This will be followed by the solutions that CST provides to address the challenging antenna design, simulation, and placement workflows. Finally, we will wrap up the multiphysics simulation capabilities as well as solutions for design of filters and other RF components. The application areas addressed by CST can be broadly categorized into 5 areas, of which microwaves RF will be the focus of today's webinar. Other strong areas for CST are EMC EMI analysis, which includes radiated emissions from PCBs, enclosures, full systems or vehicles, conducted emissions, and susceptibility of cables and connectors, electrostatic discharge, as well as electromagnetic environmental effects such as lightning strikes, EMP, etc. The EDA segment addresses power integrity, signal integrity of high-speed digital electronics, as well as EMC rule check for PCB boards. Particle dynamics phenomenon such as charged particle effects in particle accelerators, corona discharge, multipaction can also be simulated. Finally, applications such as transformers, chokes, touchscreen sensors, motors, generators, etc., would fall under the low frequency or the static segment. Our flagship solver is the time domain based on finite integration technique, and it is a robust, high fidelity solver suitable for a wide range of applications. Frequency domain solver is based on finite element method and is suitable for narrowband and highly resonant electrically small applications. Integral equation solver is based on method of moments or the multi-level fast multipole method, which is what is called as MLFMM for large structures dominated by metal. Ray tracing based method for physical and geometrical optics is the asymptotic solver suitable for very large structures for RCS calculation or radar cross section analysis, installed antenna performance, and coupling between antenna systems. Host of other solver technologies covering the full spectrum electromagnetic simulation are also available. Okay, so let us take a quick look at antennas today. Have you ever stopped to think about how your phone you to your friends or family? Is it magic? No, it's all to do with electromagnetic fields. If you think about mobile devices and their link to a cell phone tower, or of remotely controlled consumer electronic devices, or even smart appliances, the key enabling technology which provides the wireless connection between these things is antennas. Anything that has to communicate wirelessly needs antennas, and for any device to be smart, antennas are essential. Antennas and the systems behind them need to work very well every time in complex and dynamic environments. And when they don't work well, things can get expensive. And simulation is used right now for antenna design by most players in this market on the mobile device as well as on the base station side. Simulation is not only used for validation, but it is also used at every design stage from early concept evaluation to compliance testing right in the end. The reason for moving to millimeter wave is that there is a lot of bandwidth available, and this hopefully can facilitate high data rate communication. A design goal for mobile phone is to have full spherical coverage, which means gain patterns in all directions because of the user orientation and position relative to the base station. We should think about multipath effects as well and the ability to switch between multiple beams to cover full sphere. So the design goal here is high data rate communication in all situations, and the challenge is rapid antenna design for a complex and compact device. So physical prototyping is not sufficient. So the constraint which everybody has to keep in mind is the safety of the operator, and the design goal here is performance and compliance. And as you can see on the left figure here, this is basically the SAR or the specific absorption rate that is being evaluated, and you can visualize the electric fields and the magnetic fields on this phantom here. And since you cannot measure fields inside the human body, simulation is unavoidable. Now let us look at a brief chip antenna concept that is typically very exciting and interesting to be used in the 5G technology at around 28 gigahertz. So this is an antenna in package for millimeter wave, and it is a 2x2 array of stack up of patch antennas. We have dual polarization, and we can see the different layers of the package distribution network to the RFIC footprint. The hope in package is that it can be used as a discrete module Also be used in different platforms to reduce the integration process to antenna placement. And since and RF feeding required, it should be easy to integrate this into very small devices. One quickly realizes that there is more to the integration that than on the device. Power distribution network is also included in the chip. Insertion loss at 28 gigahertz, which could be as high as 0.12 dB per millimeter for strip line in FR4, which is further degraded by surface roughness. So when we look at the antenna integration in a phone, we can see here there is this phased array antenna, and you can see the radiation pattern of this phased array antenna, which is uniform. And the reason is you can see there is no back cover. But as soon as you add a plastic cover, you can see the radiation pattern is highly distorted. So it's essential to simulate to see how this radiation pattern would be affected by adding different kinds of covers. So what happens if you add a glass cover? Or what happens if you add a metal cover? And is it even possible to add a metal cover and still achieve enough radiation output? So there's a nice webinar by Mark on 5G antenna design and cover design for high-end mobile phones. And if people are interested, please contact us. If you look at why the distortion happens of the far field with the cover, it's important to understand what's going on with the fields and the way they propagate from the antenna. So you can see that the intended rate is bore side or directly perpendicular to the face of the antenna. But there are some spurious reflections that are coming off from the dielectric backplane here, which couples back into the antenna. And at 20, that acts as a waveguide. And you can see the waveguide effects where the electromagnetic wave is getting through the dielectric cover and causing further spurious resonances and radiations at the end or the corners of the phone. And this is unintended. So when we model the human body, we want to look at how the antenna performance is affected when a user is holding the phone in his hand. So you can look at the wavelength of 28 gigahertz in free space, and it's about 17 millimeters. But the body, where the dielectric properties of the tissue is very high, you can see it goes down by about 10 times. So it's about 1.7 millimeters. And if you look at the body height, it's about 1,000 wavelengths. So this is a very large simulation problem. And we need to come up with efficient and smarter methods to solve this kind of problem. So since the primary interest is the fields outside the body, we don't need to model the interior of the body. So we can actually PEC coating, and we can look at what are the fields on the surface of the body. Illustration showing a CATIA human design app on the 3D Experience platform, where you can actually pose human models to different configurations based on different use cases. And it should be very easy with the click of a button to achieve these different poses holding the phone. So once this kind of configuration is set up, it should be easy to bring in these components within CST Studio Suite and assemble them together. So this is what is being shown here. So the first block that is being dropped is the human model. And then we also bring in the phone as a separate model. And these two blocks are added together in a common assembly modeler. And this can be done using anchor points, where we align anchor points on the mobile phone as well as on the user. And we just have to snap these anchor points together. You can see the alignment is now complete, and you can then flip or rotate the phone in order to align it to any configuration that is desired. So this kind of tools allow you to very different systems together and bring it on to one assembly model. The next question is, how do we solve this kind of problem? So we can break up this into three different domains. First, we solve for the phone and the antenna being held in the hand using a time domain solver. And then we compute the near field sources near this antenna phone. And we can basically import those near field sources into another project where we have the full human body. And this way we can break down and hybridize the simulations. And it should be much more efficient in terms of computing resources, as well as simulation accuracy and time required. So the hybrid workflow hides the fine detail of the phone from the large model simulation and helps cut down simulation times without compromising on the accuracy. The next phenomenon that we should be looking at is what happens to the far field pattern of the antenna array in different scenarios. So you can see from the left, if the phone is left alone in free space, spherical far field pattern, whereas if you include the hand, you can immediately see some distortions. And if you include the full human body model of the user, you can see the pattern is heavily distorted. And it's important to understand these different usage cases. Similarly, we can look at a study where we see how the finger position can affect the array. So in this case, the finger, the orange area that you see here is the position of the antenna array, and the index finger is covering a portion of the antenna array. So we can very clearly see that there is some distortion effects comparing the index finger covering the phone or the antenna array, but then the array still should. Thus, we can evaluate potential use cases that could guide antenna placement. So antenna prototyping can be done with a tool called Antenna Magus, which is a leading antenna design and synthesis tool. It is a library of several different antennas which are already synthesized based on design requirements. So you can tweak your design requirements and quickly extract a fully parametric 3D from antenna. So you can browse through all the different antenna options available and design for your specifications. We can perform like a preliminary evaluation and then export this model to CST Studio Suite. And then you can integrate this antenna into your system and adapt it for your applications. Uh, the workflow is very unique and it is simple. So the prototyping starts with Antenna Magus, where you quickly synthesize your 3D model, and then you can export that into CST, where you can design modifications, optimizations, and parameter sweep studies. And finally, you can include a matching network, like a matching circuit to your antenna in order to match it to a particular set of frequencies or to a bandwidth. And then you can essentially take this antenna and put it on your platform, which could be an automobile in this case, to study how the install performance would be affected. Multiphysics analysis can also be done where you can study the thermal effects of heating and how that deforms the structure. So typical workflow is we start with Antenna Magus, so import CAD models from well-known CAD tools like CATIA or SolidWorks, and then bring it into CST. You can assemble these together to get a unified system, and everything is parametric by default, which means you can run parameter sweeps and study the performance of your antenna for different geometric parameters. Antenna analysis with CMA is a relatively new method for helping with antenna design. So CMA is characteristic mode analysis, and it helps to analyze and improve by understanding the antenna's behavior. You can actually create and excite useful modes to reduce coupling between the different elements. It also allows you to enhance the bandwidth, especially of electrically small antennas. This is fully integrated into CST Studio Suite and is complementary to other solvers. We can also do multi-antenna systems where you bring in the concept of MIMO, or multiple input, multiple output antenna design. So you can build arrays very quickly from a single element. So on the right, you can see there are two types of workflows. On the top is the unit cell approach, where we model a periodic boundary to a single element, and we are able to simulate an infinite array. So we can get the characteristic performance of a single element in an infinite array, and we can essentially narrow down blind spots while scanning the array. So this map gives you a picture of the active element impedance as a function of scan angle. On the bottom, you can actually build a full array starting from a single element very quickly using the full array task. So this allows you to actually define the amplitude and the phase excitations, and you can actually steer your beam based on parametric inputs. We can then install the antenna or the antenna array on different platforms. For example, here we have an automobile or a car. We can also have a ship where you have a monopole antenna radiating on the mast. We also have installed antennas on aircrafts. And all of these simulations can be done using the hybrid solution approach that I mentioned before, where we actually couple different solvers to get the most efficient output. We can look at the coupling between the antenna systems, where we look at the S parameters between these different antennas and see how much of coupling or interference happens between these systems. And finally, we can look at the far field performance of these installed antennas on these environments. When we look at the transportation and mobility industry, automotive radar is a very hot topic, and CST has the complete technology for automotive radar. So you can actually build the antenna using one of these solvers, either the time domain or the frequency domain, and then integrate the radome and look at how the radome affects the antenna performance. And finally, you can bring in this entire system into your car, where you can install this system in front of your bumper and look at how the bumper affects the final performance of the antenna. This is a real case scenario where you have two cars on a highway, and the car behind, the blue one, is actually trying to detect the car ahead of it. So you can see the rays in blue that are launched from the rear car, and these are actually hitting different parts of the car in front of it. So this is using the asymptotic solver or the ray tracing method. The ground has no effect on the radiation pattern in the azimuthal plane. So you can see the ground can be easily modeled as a thin panel sheet or a lossy surface impedance metal. The far field pattern here shows a small dip where you can actually see the target is being identified. So this is the dip caused due to the car in the front here. We can also visualize rays at different observation angles and see how scanning the rays in a certain direction gives us the reflected rays from the target ahead of us. So in this animation, you can see the blue rays are being launched from the car behind, and the green rays are the reflected rays either from the surface of the road or from the car in front of it. We can also look at hotspots or xenograms, where we can sweep the plane wave incidence at different angles, and we can look at the xenogram RCS in dB meter square. So this is a function of angle. So as you sweep the incident plane wave, you would expect different xenogram or range maps here. We can also do hotspots calculation to see which portions of the geometry are more susceptible to being detected by the radar. So the ones that are in red color are the hotspots that are more susceptible. When we look at multi-physics simulations, we can do thermal simulations where, in this case, you have a satellite reflector dish antenna, which is being exposed to sunlight on this end, whereas the other end is shadow, and the temperature difference could be very large in outer space. So this causes differential heating, and it can actually deform the antenna itself. And the deformed mesh can be fed back into the electromagnetic simulation to understand how this affects the antenna performance. So this is the coupling between the thermal solver and the structural mechanics solver. We can also look at charged particle effects, where you have a stray electron that is being released from this Horn waveguide here, and it quickly multiplies into a large stream of particles that can be very damaging. So we can study the effect of multipaction or corona discharge in space applications as well, using what we call as the particle in cell technology solver. So CST provides an end-to-end antenna solution. Very quickly start from an integrated antenna design, look at co-site interference or analysis, and finally look at SAR optimization and certification in order to study the safety to humans. So it's possible to develop and virtually validate all your new antenna concepts at a very early design stage. You can ensure compliance to functional and safety standards, and you can ensure digital continuity by seamlessly linking all these different components in one platform, which is the 3D experience platform. And CST Studio Suite is currently powered by on the 3D experience platform. Now let us switch topics and look at filters. So the main question is, why do we even look at filters? The answer to this is we should take a look at the frequency spectrum ranging from RF all the way to millimeter wave. The different bands are covered by a vast amount of applications. And today, for example, wireless communication is pushing the boundaries even into millimeter wave. As this frequency spectrum becomes more crowded, the demand for channel filters are even higher, and these can be found in all modern day wireless systems. Different technologies are used to realize these 3D filters across the majority is based on coupled resonator implementations, which produces narrow bandpass filtering. So we can have a waveguide based technology. We can do planar or dielectric cavity. For lower frequencies in the VHF or UHF, the surface mount technology is more suitable, whereas the state of the art millimeter wave, on chip and integrated filters are more suitable. So Simulia CST Studio Suite provides very good solutions for filter design, and it offers the most complete range of tools for all stages of filter design. So you can start with your synthesis, and where you actually calculate the coupling matrix between the different elements in the filter, and then you can realize this as a 3D model, and then finally tune the filter to match your performance. You can finish with a multiphysics simulation where you look at the effects of thermal and structural mechanics. We have the advanced and powerful coupling matrix, where we perform a matrix extraction using a tool FD3D. So the changes in the coupling matrix are then imported into an eigenmode solver within CST, which are then required to do changes in the 3D model for the 3D complete structure using the FEM method. Then the 3D simulation parameters, like the S parameters, can be used as an import back into your FD3D for calculating your new matrix. So this feedback loop is a very unique workflow in the market, and it provides very good advantage for filter designers. Of course, we do support traditional tuning methods, which are based on chirp C group delay or inverse chirp Z transform, port tuning, etc. So for fine tuning the filter performance, you can see the blue curve here is what we have before we do the tuning. And then we have the green curve, which is after the tuning. And this can be actually optimized in 10 steps. And we have about 18 parameters to optimize. And this is not an easy task to do, but CST can handle this very efficiently and very quickly. And one of the key enabling technologies for this is what we call as the moving mesh. So you can see on the top right corner that when you change the geometry by a very small amount, it actually remeshes the entire geometry. And this results in mesh noise. Whereas in CST, on the bottom, you can see that the mesh is not, it's not being remeshed, whereas the topology or the nodes of the mesh are slightly expanded or contracted in order to keep a very good accuracy of your solutions. So you can see that the mesh noise with and without the move mesh feature is significantly different. So the red curve is the mesh noise, whereas the green is with the move mesh on. See that the number of mesh cells required for this optimization without the move mesh feature can be dynamic and constantly changing with respect to ops. So this is a general issue in any FEM based code, while CST has this unique solution to address the filter design challenges. Finally, we can do filter tuning based on VNA. So you can connect your VNA to the laptop, which has the FD3D tool installed, and the coupling matrix is extracted from real-time measured S parameters. So you can actually visualize the errors in the coupling matrix, and it indicates how far the couplings and self-resonances are detuned in real time. So to conclude the talk for today, CST Studio Suite offers the complete technology for EM simulation of microwave and RF components and antennas. It has unique features such as a user-friendly and intuitive graphical user interface. Antenna Magus is a very nice tool for quick antenna synthesis and parameterized model export. CST also supports full bidirectional coupling between all high-frequency solvers. For filter design, we have the moving mesh feature, which is in combination is a very powerful solution. State-of-the-art HPC options such as distributed computing, GPU acceleration, and domain decomposition methods are also available in order to solve very large problems quickly. Lastly, if we ask the right questions, we can change the world. That is the message of Dassault Systems. Thank you for your attention. And I'll be happy to answer any questions.
Thank you, Narayana. Let's wait a minute if there are some questions. Let me speak in Spanish. Muchas gracias por su atención. Está disponible en el webinar. Lo pueden descargar. Es precisamente la presentación que acaba de dar Narayana sobre las herramientas de ti. Cualquier pregunta, con toda confianza, hacemos la traducción y tratamos de explicarlo de la mejor manera. Va a estar disponible en nuestro canal de YouTube seguramente en un par de días, pero si hay algún interés en particular, bueno, pues estamos para contestar alguna inquietud. Entonces vamos a dar un minuto, un par de minutos por si hay alguna duda al respecto del uso de la tecnología. Si bien estas herramientas están integradas completamente en las herramientas de Simulia, pero también disponibles en algo que llamamos 3D Experience, que es la plataforma que colaborar con diferentes aplicaciones. There are a question about the example that you show in some slides. Is in the example of the cover phone, Pablo asked if what is better, plastic, glass, or metal for this particular case.
Yeah, the question is so which cover type is better for your antenna performance, and the answer is it really depends on your situation. So plastic and glass are dielectrics, so we would need to investigate which would be better. But we also need to look at mechanical reliability as well as robustness. So depending upon the permittivity of the material, you can choose one over the other. And we have seen that materials with high permittivity in the millimeter wave tend to have these spurious effects. So we need to make sure that simulation can be used to identify which material is the best.
Okay. Another one is the biomaterials, can they be modified? You can add your own properties.
Yes. So you can define your own material properties with permittivity, permeability, conductivity information as well.
Ok, Gerardo, por ahí nos preguntaba sobre las propiedades de los materiales. Sí son editables, viene con una base de datos, pero al final es posible agregar las propiedades requeridas tanto de los materiales propios de los productos como de los tejidos y algunas condiciones de biomateriales, ¿no? Si hay alguna otra pregunta. Oscar asked if he want to know if there a way to simulate interference from another source, like when simulating 2.42 gigahertz Wi-Fi and then model another channels.
Yes, that is possible. So we have an RF interference task, which allows you to bring in different systems with different bands, and we can look at the interference. So you can define radios where you say, I want to look at the harmonic, and you can see which harmonic is actually interfering with your system. So if I actually go to this map here, we have a heat map kind of thing where you can visualize what is the level of between these systems. So if I go here, yeah, so you can see in this small tiny picture that there are some red cells, there are some green and yellow. So red means the interference is high, green is it's a go, and yellow is probably in the danger zone, so you need to be more careful. So we can get this kind of analysis for RF co-site interference.
Oscar, no sé si creo que quedó clara la respuesta. Es factible. Lo que muestra en esta ventana es una herramienta que permite determinar la interferencia y cuál es una especie de semáforo. Del rojo indica que pues, hay interferencia, verde este, es libre y amarillo probablemente exista, ¿no? Perfecto, gracias. Ya vi tu respuesta. ¿Alguna otra inquietud? Bien, de cualquier manera, nuestros canales de comunicación quedan abiertos para todos ustedes. Narayan, I think that's all. Thank you for your webinar. I think later could be some question for the audience, and I share if we receive something about that.
Okay, thank you very much for everyone for attending, and have a nice day.
Que tengan muy buen día todos. Hasta luego.